Good morning, guys. Now we'll start our next lecture. In this lecture, we will solve one example related to your spring system. Okay. In previous lecture, we have solved some examples regarding your constructing your global stiffness matrix and applying the boundary conditions. Then you will get the you will apply the elimination approach to get the displacement and force or reactions values. So similar way, we will solve some example. Okay. So this is the example. Actually, I have given this example as a homework for you guys in previous lecture. So I will try to solve, or we will actually, if you had any doubts, then we will clear it here only. Okay. So we will solve this previous example. Actually, we have discussed this previous example regarding this spring system as this is the example that we have. Actually, I have given you for homework. This is the example. This is the parallel spring system. Two ends are fixed. First stiffness coefficient is 200. For this is 400. This is 600. This is 800. And last one is 1000. Okay. And as they have mentioned also the nodes 1, 2, 3, and 4. These are the nodes they have given. Also a 10 kN of force is acting here. 10 kN of force is acting at node 2. And they asked to find out the displacement values. First one is displacement at node 2 and 3. And second one is find out the reactions at support. Okay, so these are the two questions they have asked. Actually, this example is asked for 6 marks in exam examination. Okay, so we will try to solve this example. Okay, actually, if you have any doubts during solving this example, that we will clear it in this your lecture. Okay, so we will start this lecture and try to solve this lecture. So first step was, actually I have discussed all the things in previous lecture, that there are 4 nodes, means your global stiffness matrix will become of order 4 by 4. Means you need to first evaluate or first find out the elemental stiffness matrices. Then you need to construct this global stiffness matrix by using these elemental stiffness matrices. Then you need to apply the boundary conditions. Then you will get the displacement value. Means by eliminating, you will get 1 or 2 equations, and by solving these 2 equations, you will get the displacement value. And by putting these displacement values into your force equation, you will get the reactions. Okay. So similar way, we will solve this example. So first, you need to convert this parallel spring system into one spring. Okay. So as we know that this spring system is converted into one spring system as addition of these spring coefficients 400 plus 600 plus 800. Okay, so it will become 6 plus 4 1000, 1000 plus 800 1800 Newton per. Similarly, let's say this is Newton per. Okay, so in this way you will convert your parallel system into one spring system or equivalent spring system. Okay, so this is converted as equivalent spring system as its value is equal to 1800 Newton per meter between node 2 and node. Okay, now we will proceed our first step. This first step was find out the elemental stiffness matrices. So elemental stiffness matrices, as we know that the standard elemental stiffness matrices in terms of K is given as K minus K minus K. Okay. So in this way you can convert your spring system by using this elemental stiffness matrices. So as E1 for this spring system, first elemental stiffness matrices will become E1 is equal to, so instead of K we need to put 200. So it will become 200 minus 200 minus 200 200. And the position of this elemental stiffness matrix E1 is between node 1 and, so between node 1 and node 2. Between node 1 and node 2 means you need to put this elemental stiffness matrix between rows 1 and column 1 and. Similarly, E2 will become, so E2 for this coefficient, stiffness coefficient is 1800 Newton per meter. So it will become, instead of K, put 1800. So 1800 minus 1800 minus 1800 1800. Okay. Then similarly E3, but we need to put the position of this E2 also. Okay. So the position of E2 is between node 2 and node 3. Okay, so between node 2 and node 3. Between node 2 and node 3. Then last, third elemental stiffness matrix will become 1000, 1000, minus 1000, minus 1000 and 1000. Okay, so, and the position of this E3 is in between node 3 and node, between node 3 and node 4, between node 3 and node. Okay, so in this way, here the elemental stiffness matrices can be calculated. Okay, now next step is to construct the global stiffness matrix. As we know that there are 4 nodes, n is equal to 4. So your order or global stiffness order will be, global stiffness matrix order will become from 4 by 4. This is, it should be a square matrix of order 4 by 4. Okay, so now construct the global stiffness matrix as, so K is equal to, the positions are between node 1, 2, 3 and 4, between node 1, 2, 3 and 4. Okay, so in this way, now you need to position this E1 into this global stiffness matrix. Means, as we know that E1 it will lie, actually it is lying between node 1 and 2, between node 1 and 2. So the position will become between node 1 and 2. Similarly, E2, the position of E2 will become between node 2 and finally the position of E3, it will become between nodes 3 and 3 and 3 and, so it is between 3 and. So simply now you need to just put down these elements over this block. So first it will become 200 minus 200 minus 200 and 200. Similarly, second block 1800 minus 1800. So here it will become plus 1800 minus 1800 minus 1800 and this will become 1800. Then finally last one is 1000 minus 1000 means you need to put this E3 over this block. So it will become plus 1000 minus 1000 minus 1000 plus 1000. Okay, and remaining elements will be equal to 0. Okay, so in this way you will get the global stiffness matrix. So simplify or finally you will get the global stiffness matrix as K will become equal to between node 1, 2, 3 and 4. So it will become 1, 2, 3 and okay. So 200 minus 200, 200 minus 200, 0, 0, minus 200, 1800 plus 200, 2000, then minus 1800, 0, then 0, minus 1800, this 1800 plus 1000, 2800, minus 1000, 0, 0, minus 1000 plus 1000. Okay, so in this way you will get the final global stiffness matrix. Now what is the next step? The next step is write down this global stiffness matrix in the form of your force and displacement relationship. As we know that the force and displacement relationship is given by force vector is equal to K times global stiffness matrix times your displacement vector. Okay, so you need to just note down that U1 displacement is U2. Similarly, at node there will be U3. At node 4 there will be U3. Similarly, force nodal forces will be there also. So this will become F1, F2, F3, and finally F. Okay. So now you need to write down this force and displacement relationship by using this global stiffness matrix. So as we know that as there are 4 nodes, so there must be 4 equations of 4 nodal forces. So first one is F1, second one is F2, third one is F3, fourth one is F. Okay. And into displacement vector as U1, U2, U3 and U4. Okay, so in this way you can write the force vector and displacement vector relationship. Now next step is what? Apply the boundary conditions. Okay. So first apply the boundary conditions for displacement, then apply the boundary conditions for forces. So first the boundary conditions for displacement. So as first node is fixed one, so at this node there will not be occurring any displacement. So U1 will become 0. Similarly, at node 4, this node is also fixed one. So at this node also there will not be any displacement or any movement of this node. So U4 will become 0. Okay. So U1 will become 0. U4 will become 0. Finally, U2 and U3. Because U2 and U3, there must be some displacement because these nodes are not free. These are not fixed ones. So at this node 2 and node 3, there must be some displacement. So U2 and U3 are the unknowns. Okay. So our displacement boundary will become U1 is equal to 0, U2 is equal to question mark, U3 is also equal to question mark, and U4 is equal to 0. As we know that U1 and U4 are the fixed one, so it will become it must be equal to 0. Now next is what? Apply the boundary conditions of forces, means apply the boundary conditions for force vector. So as we know that F1, this F1 it is fixed one. So at F1 there must be some reaction force R1. Now at node 2, F2 is there, but at node 2 they have not mentioned any force, any type of force at this node. So it is not given, so it must be equal to 0. So F2 will become 0. Now F3, sorry. Instead of at this node actually some force is given, sorry. In previous, in parallel system, force of 10 kilonewton was given. So F2 will become 10 kilonewton. Actually, in your example, this force is given at node 2. 10 kilonewton of force is acting at node 2. So there, that's why your F2 will become 10 kilonewton. And at node 3, there is no load or no force. Okay. So in this way, it will become 0 as they have not mentioned. So you need to assume equal to 0. And last one is your F4. Now you know that this is also fixed node. So at this node there must be some reaction. F4 will become equal to R. Okay, so in this way, your boundary condition will become F1 is equal to R1, F2 is equal to 10 kilonewton. 10 kilonewton means 10,000 Newton, because your coefficient of stiffness is in Newton per meter. So you need to take this F2 in Newtons. So F2 will become 10,000. F3 it is equal to 0 and F4 is equal to R. Okay, so in this way your force vector will become. Okay, so this is your R1. First one is R1 1000, 0 and R1. So this is the final boundary condition. This is your 10,000. Okay, so R1 10,000, 0 and R1. So in this way, you have constructed this relationship between force vector and displacement vector. Now, next step is what? Apply the elimination approach. Okay, so how we are going to apply the elimination approach? As we have discussed in this elimination approach in previous lectures, that first find out the displacement value. Where the displacement is 0, you need to eliminate this row and this column. Okay, so in right hand side, where is the displacement? The value is 0. And this first row, this first row and first column. So u1 is equal to 0. So you need to eliminate this first row and first column. Okay, so you need to eliminate this first row and first column, because u1 is equal to 0 at right hand side. Similarly, u2 is unknown, u3 is unknown, and u4 is equal to 0. So you need to eliminate this u4 also. Means you need to eliminate the fourth row and fourth column also. So fourth row and fourth column. Okay, here first row and first column. So here only two equations will be remaining. Okay, and these equations are 2000 times u2 minus 1800 times u3 is equal to 10,000. The next one is minus 1800 times u2 plus 2800 times u3 is equal to 0. Okay, so after eliminating the rows and columns, you will get two remaining equations. Okay, so by using these two equations, you will get the unknown values for displacements u2 and u3. Okay, so just write down these two equations. 10,000 is equal to, here I am writing these two equations. Okay. Here I am writing these two equations. 10,000 is equal to so two equations will become 10,000 is equal to 2000 times u2, 2000 times u2 minus 1800 times u2 minus 1800 times u2. Second one is 0 is equal to minus 1800 times u2 minus 1800 times u2 plus 2800 times u3. 2800 times u3. So in this way you will get two equations. Now by solving these two equations, you will get the values for u2 and u3. Okay, so solve these two equations in your calculus by using two unknown constants. In your equation type, you will get u3, u2 and u3. Okay, so u2 and u3 will become equal to, u2 is equal to 11.86, mm, and U3 is equal to 7.62. 62. So these are the final displacement values for your displacements or displacements at node 2 and node. Okay, so in this way you will get the displacement values. Now the next question is for to find out the reactions at support 1, also at support 2. Okay, so to find out the reactions we need to take the reaction equations, okay, from this force and displacement relationship. So here we know that this R1 is equal to this equation, means this value is into this value. Similarly R4 is equal to this into this. Okay, so as we know that U2 is equal to 11.86 mm and U3 is equal to 7.62 mm. These are the two displacement values. So by using these displacement values, you will get the reaction at node 1 and at node 4. So by writing this equation as R1 is equal to 200 times U1, but U1 is equal to 0, so it will become 0, minus 200 times U, minus 200 times U, 0 times U is plus 0, plus 0 times U, plus 0. Okay. So in this way you will get R1 is equal to minus 200 times U, so minus 200, and as we know that the value of U is 11.86, so it will become equal to actually the values here it is not given, so it will become 6 into 2 12 1 8 into 2 16 plus 1 17 1, then 2 into 1 2 3 2 into 1 2. Okay, so it will become 0 0. This is the final value, Newton, 2372 newtons. This is the value. Okay, similarly R4, from R4 you will get R4 is equal to 0 times U1, 0, plus 0 times U2 means plus 0, minus 1000 times U, minus 1000 times U2, and plus 1000 times U4, but U4 is equal to 0, so plus 0. So R4 will become equal to 0 plus 0 means 1 minus 1000 times U. As we know that minus 1000 into U3 is not, it is equal to 7.62 mm. 7.62. So it will become equal to 7620 minus, actually this value will become minus Newton. So first one will become 2372 and second one will become 7620. Okay, so R4 will become 7620. So in this way you will get R4 7.62. 7.62 into 1000 means 7620 Newton, and R1 will become 2372 newtons. So in this way you will get R1 and R2. Now just cross check the values here. So as we know that this was the spring system. Okay. At this node 2, a force of 10,000 Newton was applied. Then R1, value of R1 is 2372. 2000 minus 200. The minus 200 is minus. This is minus. Because minus 200 was there. So minus 200 minus 200 into 11 it will become minus 237. So it will become minus 237. It is applying in this direction. 237. Because the value is negative. So it is applying in the opposite direction. As we have taken positive in horizontal right direction. So it will be in negative direction. 237. Similarly, 7620. So it will also act in this direction. 762. So finally, you will get this 10,000 Newton is applying in this direction, and it is balanced by these two reactions, 2372 and 7620. Actually, 7620 plus 2372. So it will become round figure equal to 990. Okay, just because of some approximations, this value is equal to 9,992 newtons. Means it is equal in magnitude and opposite to this 10,000 newtons. Means your answer is correct. Okay, so in this way you can cross your answers also. Okay, so in this way you will get the displacements and your reaction values. Okay, so in this lecture and or now we will conclude this spring system, one-dimensional spring system, with this lecture, because in previous 2-3 lectures we have discussed the problems, derivation, as well as how to construct the global stiffness matrix for one-dimensional spring element. So now onwards we will solve, or we will just derive the stiffness matrix or global stiffness matrix for one-dimensional bar element. Okay, as in this lecture we have discussed, or in previous 2-3 lectures we have been discussed about your stiffness matrix for one-dimensional spring element. Okay, so in this spring element, just K is the spring coefficient. By using this K value, you will construct the global stiffness matrix. But similar to this spring stiffness matrix, we will construct the global stiffness matrix for one-dimensional bar element, and we will solve the one-dimensional bar problems by using this same procedure. Means first elemental stiffness matrices, then next you need to construct the global stiffness matrix, then next you need to apply the boundary conditions, then next apply the elimination approach, and by using this you will get first the displacement, and by using the displacement value you will get the reaction or forces value, and by using this force value you will come to know the stress value. Okay, means first you will get displacement, then you will get forces. Okay, so from this you will get strain, from this you will get stress. So we will apply this procedure, same procedure, to one-dimensional bar element, and by using this same procedure we will find out the stresses and strains in the bar element. Okay, so here I will conclude this lecture, and in next lecture we will start our one-dimensional bar system. Okay, thank you.